Share the screen, make sure you don't forget any steps. Come over here. Okay, welcome everybody to data mining. We're gonna start going over the exam today, and then we'll get back into the regular material. The answer key to the exam posted in the exam folders under this midterm1.pdf file. And your particular grades all posted into Sakai, along with notes about what you did correctly or incorrectly on each of the problems, how I scored each of the problems. And let's see, first thing for us to go over with that here is the grade distribution. Overall, very high grades in the class. Over here, out of these things in the 90 to 100 range, there were 15 people who not only got perfect scores on the exam, but actually got the 16 out of 15, and I had to truncate your score down to 15. So I was very pleased with that. It's a little bit over half the class getting perfect scores. Median grade 14, so that's in the A range. Average grade 13, so high B. If for whatever reason your grade is not what you want it to be, then recall, first of all, that your grade on the final exam, the very last exam we have in the class, will be an in-person exam. And whatever you get on the in-person exam will be able to replace your lowest grade in the class. So that's the first thing about that. The second thing about that is that if your grade is a 70% or less, and you would like to bump it up to a 70%, then you can schedule an in-person time with me to explain to me all the things that you missed about your exam. And if you convince me that you now understand the material, then I will increase your grade up to 70%. I don't think I actually made a GitHub issue for that with the details yet, but I'll do that so that you have a written explanation of that. But it's just schedule a time to meet with me and convince me that you know all the material that you missed. And if you convince me, I will upgrade your grade from whatever it is up to a 70. We're going to go over the actual material here, the answer key for the exam next. Here we go. I have it opened up. And again, on GitHub, you can find it if you want to look at it later. It's in the exams folder, the midterm1.pdf. I just replaced the old file with the answer key. And here we'll start going over the exam, going from back to front. And so this very last one, describing a problem using PageRank. I was basically, if you had something remotely reasonable there, I gave you full credit on this problem. And so I want to take a second here to get a little bit maybe meta about how, like what I feel like is the purpose of exams and assignments in general. A lot of professors when designing exams or designing their course, they divide up their course into like assessment period of the course and learning period of the course. I hate assessment period of the course because it's just a waste of everybody's time if there's no learning going on. So I try to make sure that all of the things that happen in assessment somehow are related to learning. And so the reason for having something like this here is just to make sure that, like, after graduating, after going away from this class, maybe the one important thing to take away from PageRank is when you might apply it. And so this is, if there's a most important problem on the exam, this is it. Also probably the easiest problem on the exam. And yeah, so that's why we're starting at the best too, because start with the most important. Second one, problem 6 right here. Another problem that's super important from a pedagogical perspective of what to take away from this course. This idea of like somehow splitting long matrix multiplications, matrix exponentiation, splitting it up into this divide and conquer step, something that comes up all the time. And another just like good thing to remember, that anytime you have a lot of matrix multiplications going on, if it's the same thing, you can always split it up with the divide and conquer. If somehow you mentioned any sort of divide and conquer-ish looking thing, then I give you full credit on this problem. Nobody pointed this out, but technically this k up here that can be any positive integer. We only talked about it for 2 to the k, something positive integers that are powers of 2. This is the most correct solution down here for computing for any k instead of just powers of 2. But it's super technical detail, so gave full credit for anything that looked remotely like what we did for the EAPM. Problem number 5. In practice, no one uses the APM to compute Bayes-Rigged vectors. Why? I accepted a lot of different things about here. As long as somehow you were talking about the size, like this in factor over here being way too big, then you got full credit on this as well. Yeah, people who missed all these last problems, there was no partial credit awarded for anything. People who missed things usually like way down the wrong track on something totally unrelated. As an aside, if for whatever reason on your exam, after you've had a chance to look over it, look over the answer keys, look over my notes in Sakai about what your grade is, if you think I might have made a mistake during grading, let me know over email or just in person at some point, and I'd be happy to reconsider your grade on any particular problem if you think I made a mistake. Let's see, going back up here now to problem number 4, that one's based on problem 3. So we'll start with 3 on this runtime right here. So the key idea here, the slowest of these steps is this matrix vector multiplication. That's quadratic. So an O of n squared. If you somehow totally missed that, didn't put an O of n squared, then you got no points on the problem. If there was an O of n squared somewhere, but you also had a lot of other stuff inside of here, you got partial credit, half point. The whole point of using the big O notation is so that we can simplify it and just keep the important terms. And then this solution problem 3, important in number 4, it's one of the steps to it. And now this big O right here was the full credit solution. If you made a mistake in the previous problem and you carried that mistake over, then you got half credit. Or again, if you didn't simplify for whatever reason, then you got half credit. On none of these problems so far was I looking at any sort of, or you didn't require to have any sort of work shown, and as long as you had the right answer indicated somewhere, then you got full credits. Let's see, any questions so far? Okay, number 2. So I accepted a lot of possible things as answers on number 2. Technically, this is a false statement right here, and there are half the class or so provided counterexamples showing that it was false. Here's an example of a counterexample. I, in class, made a mistake with one of my explanations of things, talking about the difference between the eigenvalues and something called singular values. The full explanation of that is down here if you would like to read it. But this short explanation is that for most matrices that we care about in data mining, the singular values are equal to the eigenvalues. And somehow I got that in my head and said that this thing right here, this L2 norm of the matrix, is the top eigenvalue. Technically, it's the top singular value, which is not always equal to the eigenvalue. And in this particular matrix, doesn't have to be equal to the eigenvalue. So anybody who somehow took advantage of my mistake also got full credit on the solution, even if you said that the answer here was true when it's actually false. So I apologize for that mistake, but I think overall it lifted people's scores up. So maybe you're happy I made a mistake. The main spot where people missed most of the points on the exam was the true and false, especially these true and false questions that involved asymptotic notation somewhere inside of them. The vast majority of points missed, probably like 80% of points missed, happened on the true and false with the asymptotic notation. So if you have any questions about why these are the answers that they are, you should get those clarified before the subsequent exams, because you'll need to know that information for the subsequent exams, even if we don't have like these sort of exact same questions on there. Similarly, because of the mistake I made with the eigenvalue, singular value distinction before, I decided to throw out problem 4 right here that was based on this. And so everybody got a +1 point on this problem, whether no matter what answer you did or did not put on it, you got +1 point. Any questions about anything related to the midterm? Okay, if questions do come up later on, then you should definitely feel free to email me them or come see me in person. That said, we're moving on to pick up where we left off last class period. And again, this is in the sort of between chapters 1 and 2 notes. We ended off drawing a graph that looked something like this. And while everybody's getting those things out, I'll just say a little bit more from this like meta perspective. I guess first of all, I like to sometimes talk about meta things, like my perspective, teaching why I do things a certain way, because one of the things that's good for you all as in general in life, whether you're a student or at your first job, you should always, one of the best pieces of advice I ever got was think about like however your boss is doing their job, how could you do it better than them? Try to do be able to do the job that your boss is doing, and that when you're like actually at a company will help you get promoted faster. People will see that you're able to take on those responsibilities. And so here, one of the things or one of the ways that you can practice that is think about how your professors are doing their job and how the decisions they're making and whether you can make those decisions better or not than them. So that's a big preload to one of the ways that I'm structuring these notes is so that we never quite finish them at the end of one particular lecture. We always have a little bit left to do to help us review the material from each of these sort of note packets, that the packets themselves are sort of self-contained, but by spreading it over 2 days, you get twice as much exposure to the material, and hopefully that helps you absorb it a little bit better. This problem number 3 right here, this is a key graph to remember. If there is like one thing to remember from this whole section of the class, this period coming up to the second midterm, it is this graph right here, where the x-axis is somehow like our measure of the model complexity. So far, the model complexity that we're talking about is the size of the finite hypothesis class. So that's what this M variable right here is. The capital M is the size of our hypothesis class. And it really only makes sense to talk about the size of a hypothesis class if it's finite, because if it's infinite, then it's infinite. And this red line here, this E sub n, again, E sub n, the n stands for the n sample error. I often will say training error because it's the error on the training set. And it's more common in the data mining world for people to say the training error than the in sample error, but the book calls it the in sample error, the E sub n. So anytime I'm writing it out in notation, I'll always say E sub n. And as your hypothesis size gets bigger, then the intuition is that your training error goes down because we're adding more and more possibilities of things that we can select from, more hypotheses that we can select from. And so we're more likely to get a good one, more likely to have one with the training error low. This orange line right here is the generalization error that we don't really care about this in sample error. What we really care about is the out of sample error, the E out. This is the true error of our problem. And this is something that we can't measure directly at all. All we can actually measure is the in sample error, the EN. And so we put bounds on this EN minus E out, this generalization error right here. And our bounds that we've talked about so far for the finite hypothesis class generalization, this theorem 1 right here, the FHCG theorem. the bounds look something like this, where the generalization error somehow depends on both m, the size of our hypothesis class, and this n, the number of data points that we have. And in particular, as m, the size of the hypothesis class increases, then our generalization error also increasing. So this orange line going up, and then this green line being somehow like the sum of these two lines. And so there's some sort of like key spot in the middle here, some ideal size of a hypothesis class that we want to pick from. Any questions on any of the notation or anything that we've seen so far? Yes.
So just to like sort of recap more, like you want like E out is like the predicted performance on like a set of data that the model's never seen before.
Yeah, exactly. So the out here standing for out of sample performance. So you can sort of we talked about the test set. The test set is like an approximation of this out of sample performance, but it's like the future things that we haven't seen yet. With our credit example, this would be like people. So the year's 2022 right now. Maybe in 2023, people will still be applying for loans probably. And so there's no way that we could possibly have the data available from 2023 yet. And this E out is somehow a measure of that future performance on that data that may not even exist yet.
So does it also take into account like the possibility of like let's say like a coronavirus or something happening, or like pre-standard deviation events happening, or is it like just like the best estimate based on?
So the question is, does E out somehow take into account like what the sort of formal thing is a shift in a distribution, some sort of major event happening possibly that causes what is good credit versus bad credit from changing? The answer is, at this point, we haven't talked about that at all, that this E out is specifically assuming that the EN is assuming that all of our samples are generated from the same distribution that we're trying to measure on E out. That there's only one distribution involved here, and it's constant throughout all of time and all of space and the entire universe. Machine learning and data mining people definitely consider that what happens when that distribution changes. But in order to understand that, we really have to understand the simple case of the distribution being the same first. And there's a lot to unpack with just the distribution being the same. Good question. Any other questions so far? Okay. So I mentioned that in the data mining world last time that people don't really, certainly in practice when we're computing things or working on problems, we don't care about like specific numbers at all. What we care about is somehow trends in numbers. And the use of specific numbers is maybe just to help us get like an intuition for how those trends might work. But I'm never going to ask you on the midterm to like calculate with specific numbers. So that said, we're going to do a calculation with specific numbers again, just to help us build that intuition about these sorts of trends. And so the idea in this problem, I have, let's go ahead and close this over here, that we have some particular set of dimensions, some particular number of data points. And the idea is we're going to use the theorem above to bound the number of samples or to bound the size of the hypothesis class. So due to the small amount of training data, only 500 data points, we're deciding not to create a split into training and test sets, and we're just going to use the entire data set for training. And in our particular application, for whatever business like purpose out of our control, the generalization error should be less than this with probability at least 0.99. So using that, just repeating what's up here, I want the probability that E in minus E out. Ah, and sorry, I closed that too soon. That is less than or equal to epsilon. That should be greater than or equal to 0.99. Here, my theorem above was not about the less than or equal to. The theorem statement was about greater than or equal to. So I'll say that this is actually equal to 1 minus. It's a probability. There we go. Convert that mark into a parenthesis. The probability of E in minus E out being greater than or equal to epsilon, which by the formula that we had above is greater than or equal to 1 minus 2m x of -2 epsilon squared in like that. And I'm going to set this. Our goal is to have this probability being greater than or equal to some value delta. So greater than or equal to delta like this. And we're going to solve this inequality right here for delta. Or sorry, we're going to solve it for m so that we know how big our hypothesis class can possibly be. So doing that, we get that m should be less than or equal to 1 minus delta divided by 2x -2 epsilon squared in like that. And yeah, I don't know, the symbol manipulations that go from here to here. I trust that you can all work out. But this is going to be the final formula that our m, the size of our hypothesis class, needs to satisfy. And also last time, I don't know, people were, I don't want to say complaining that I made arithmetic mistakes, because that's not a thing to complain about. But I'm just going to avoid arithmetic mistakes by typing things straight into Python. And I assume everybody here has the terminal bound to a hotkey on your computer so that you can open up Python instantly and do some math. Import math, we'll say. So this is our formula that I have to compute. So start with just 1 minus delta divided by 2 math dot x -2 times epsilon squared times n like this. Started off giving me all this 2 times math dot x, giving me a whole bunch of errors. Variables not defined. The delta should be 0.99 with probability at least 0.99. Copying that from the problem up here. That epsilon I said should be 0.1, 0.1. And then the n, the number of data points, 500, n equals 500. Back up to get to that formula, hit enter. And so m, as long as m is less than or equal to like 110.1, but m is the number, size of a hypothesis class, so it must be an integer, so it has to be less than or equal to 110. Then we'll be good. Control D, exit out of Python, exit out of the terminal. So this is, if I want these sort of constraints up here, this is the size of the hypothesis class that I can choose. And so the question specifically asking which of the above finite hypothesis classes can I use? And so we're going to scroll back up, look at the different finite hypothesis classes that we have and see what their size is for the dimensions equals 100. So I'm going to scroll back up to the top where we had this list of finite hypothesis classes right here. And we previously talked about the size of all of these hypothesis classes. And so here we have m equals 2. If I substitute for d equals 100, this implies m equals 2, m equals 100, m equals 200. And then down here, I got m equals 2 to the 100 and m equals 3 to the 100. And the thing that like is jumping out to me is that like, okay, 100 and 200, like, so literally this is the dividing line right here about these two hypothesis classes are things that I can choose. These ones down here are things that I can't choose. But like jumping out to me, like 200 and 100, those are pretty similar numbers. But m to the 2 to the 100, that's just like a ridiculously larger number than 100. And so it might not be too bad to try something like this h-axis 2 hypothesis class, but I can be pretty confident that like these other ones down here are just like so far out of the ballpark that there's no point in even considering them at all. And this sort of like, eventually we're trying, like the purpose of what we're talking about here with these theorems is we're going to be building up an intuition about when I can just like totally disregard certain types of hypothesis classes because their size is just like way, way too big or way, way too small for the particular problem that I'm thinking about. So at this point, we're not quite ready to like fully do that on an intuition level. There's still more things that we have to see, but that's what we're building up to. But so in this case, the literal two answers are the H binary and the H axis. So coming down here, the literal answers that satisfy this would be the H binary or the H axis like this. And then of these hypotheses that you can select, which one should you select? And we talked before about like the binary is just like a really, really dumb hypothesis. It doesn't even consider the data in any format. And so we don't want to include this one. We would want to select the h-axis. This one at least considers the data in some context, in some way. So again, what we're building up to with this next series of content is being able to do all of this at an intuitive level. If you remember, like the very first lecture in class, we sort of looked at the scikit-learn library and looking at the documentation, it turns out there's actually like thousands or hundreds of thousands of different hypothesis classes to choose from. And so somehow being able to like, for our particular problem, being able to zoom in onto which ones might possibly be reasonable is our ultimate goal here. So if that's not like, how do you do this at an intuition level? If that doesn't make sense yet, that's okay. But are there any questions about like either what we've done or where we're going? Kieran first.
So it's saying like, let's say we have like 110 hypotheses classes then, right, for this one problem?
The correct statement is that the h-axis, the size of h-axis, the size of this hypothesis class equals 100. And because this size is less than our maximum possible size, we're allowed to choose it.
Okay.
So this isn't the number of hypothesis classes. This is the number of hypotheses in a hypothesis class.
Okay. So does that mean like if you were doing a classification problem, is it drawing like 110 different planes and testing which one works best?
So one of the, I'm pausing right here before answering this question because one of the like fundamental assumptions that students often come into with questions is talking about what something is doing. And we need to get away from like the idea of what something is doing. At this point, we're not talking about anything algorithmically. We're not talking about any like procedure for doing something. Instead, we're putting limits on what any procedure possibly might do. And so we're not talking about what something's doing, we're talking about what something is allowed to possibly do. And so what something is allowed to possibly do is look at up to 110 things. Whether it does look at what the final procedure that you do choose to use, whether it looks at 110 or whether it looks at some smaller number is up to that procedure, but something that we haven't talked about yet. I guess we did talk about, so we've seen two different of these training procedures that actually talk about what something is doing. The first one was that PLA algorithm for the perceptron learning algorithm. That worked with an infinite hypothesis class. The second one is this try everything algorithm, which literally tries every hypothesis in a hypothesis class to see which one's the best. The try everything algorithm will try them all. So it will try all 100 of the hypotheses in h-axis if this is the algorithm that you're using. But the result down here is not making any assumption about what algorithm that you're using. You could use some other algorithm like select a hypothesis class at random, and everything would stay true for what this is saying. So I don't know if any of that answered your actual question in there somewhere, or if I just ignored it. Okay. Yeah, and again, one of the difficulties of this whole section of the class right here is just how abstract everything is. And before we can, things are just going to keep getting a little bit abstract over the next week or so. And then once we've seen all the terms, seen the theorems that we need, then suddenly things will get significantly more concrete.
How can you actually get this to
Yeah, exactly. So the thing that we're building to is how can you get the intuition of selecting things like this without actually plugging in numbers? And the answer is that's what we're building to, yeah. So actually, and that leads us to the second problem down here. This is getting a little bit more into the intuition because there are no numbers in this problem. And so this is closer to the sort of thing that people actually do in real world data mining problems. And this is the sort of question that might possibly appear on a midterm. So here it's saying given two finite hypothesis classes, H1 and H2, we don't know what they are. It's just any arbitrary two classes, could be some from the list that we've seen above, or they could be something totally different. There's this procedure right here for constructing a third hypothesis class. Just consider the third one could be the union of the previous two. The hypothesis classes again are sets. So this is just your hypothesis can be everything in the first set or everything in the second set. So this is a very common thing to consider in practice, that you have two different learning models and you'll try them both and see which one's the better one. And that's this H3 right here. We're saying for each, so this G sub I is the result of running the T algorithm on hypothesis class H sub I. So recall that the T algorithm computes G sub I equals the arg min over H in whatever H sub I we're considering of the E in of H like this. This is the definition of what the T algorithm does from above from the last class period. And again, it's just going to try all of these hypotheses, just figure out which one is the best and pick that one. And so the actual question right here is, how does the in-sample error of G3 compare to the in-sample errors of G1 and G2? So the in-sample error is this E in right here. So E in of G3, my claim is that it must be less than or equal to the E in of G1. And separately, this is a totally separate statement, E in of G3 must be less than or equal to E in of G2 like this. This green thing here is my claim. And so the question is why? Why must something like this be true? Anybody have a guess? The thing on the left-hand side of this inequality in both cases is G3. And then on the right-hand side of the inequality is G1 and G2. So the thing on the left-hand side is the union combined, and the thing on the right-hand side is the individual hypothesis classes.
Sorry, what's the thing? That's right under our.
This is a lowercase h contained in the funny scripty h sub I. So that sub h sub I could be the hypothesis class 3, hypothesis class 1, or the hypothesis class 2. And this formula, again, comes from the T algorithm definition.
So, for the first one, for example, like you're taking the minimum, like in error from like H and HI. And since H3 is the combination of those two, it could union those two, then like if you're taking the minimum from H3 to H1 and H2, it can't be greater than the minimum from H1. And same for H2.
Yeah, exactly. So restating here what Chuck said is that here, this G1 right here, G1 came from H sub 1. So we know that G1 must be inside H sub 3. We know that this G1 must be inside H sub 3 because it's inside H1, and everything inside H1 is also inside H3. And so when we do this, this argmin over H3, we're going to consider the G sub I at some point. And so whatever we end up selecting from the argmin, since we did consider this G sub I, it's either better than or equal to G sub I. It's not going to be worse. And the same argument holds here for G2. For something like this, there's no need to provide some sort of like step-by-step proof of how you came up to a conclusion like this. Just stating the final result is the important thing. And so, like, how is this important in practice? Well, if we have a learning problem and we have a bunch of hypotheses to select from, and we know that our training error is somehow going to be like really important, is going to be the hard part of the problem, then we should select the hypothesis that's the biggest, that's going to contain the most things, so that it has the smallest amount of training error. These formulas right here, these two green formulas, they're basically saying the same thing as in this chart over here. What this red line is saying is that as your hypothesis size gets bigger, the training error can only go down. It can't go up. Conversely, this part 2 down here is talking about the generalization error instead of the training error. And so this is E out of G3 based on this FHCG theorem, this finite hypothesis. Where did it go? This one right here, this finite hypothesis class generalization theorem, then we know that as this M value gets bigger, the M value for H3 must be at least as big as H1 and 2. So this is getting bigger. So our generalization error is going up. So here when it talks about the generalization error, that's the E out minus the E in of G3. We know that that must be at least the E out G1 minus the E out G2. Whoops, both of these should be ones right here. And then again, as a totally separate statement, E out of G3 minus E in G3 must be greater than or equal to E out of G2 minus E in G2, like that. And one more little typo mistake that I made is that this out right here should be an in. There's one out and one in, and each of these formulas, and it doesn't matter which order you put the out and the in because it's the absolute value. So the order doesn't matter. But if somehow you know that the generalization error is the hard part of a particular learning problem, then now it makes sense. You don't want to pick the hypothesis class 3 because it has the bigger generalization error. Now you would want to pick H1 or H2 to do your learning on. Any questions about any of that? So the way that these inequalities, where they came from, is that I know, first of all, I'll do it in red right here. I know that the size of H3 must be at least the size H2, like this. And I know this because H3 contains everything inside of H2 plus everything inside of H1. And up here, similarly, I know that H3, that size is at least the size of H1. And these H's right here, these H's are the size of, the size of H, that's equal to, that's the meaning, the semantic meaning of the M in these formulas right here. And looking at this formula, I can see that the generalization error here is going to get bigger as M gets bigger. As the number of hypotheses gets bigger, this error over here is going to get bigger. It's a little bit easier to see down in this formula right here that doesn't explicitly express probabilities, but the E out minus the E in, that will get bigger as M gets bigger. And because of that, because this M value for H3 is bigger, I know that the generalization error must be bigger based on that, on those formulas. We're going to see a lot of variations on these different inequalities that we've put here over the next week or so as we start transitioning from the finite hypothesis class to the infinite hypothesis class. In some sense, the finite hypothesis class is easier because finite things are just easier than infinite things. And so they're a little bit more concrete. You can actually count things. But in some sense, it's a little bit harder because the finite things are also very toy things and not things that you're probably going to use in real life. But the infinite things are things that you're more likely to use in real life. And so the intuition behind the big picture purpose can sometimes be more clear on the infinite things. So if this whole page is like just a total blur of random Greek symbols, then think about revisiting it in a week after we've seen more examples. I'm going to come back up here now, and I want to talk a little bit more context about these formulas up here, and especially this bottom form of this formula right here. And I want to, I'm going to rewrite this formula in a different way. These two formulas up here are exactly taken out of the textbook on these pages. The thing that I'm going to write right now, not taken out of the textbook, but I think captures the intuition about things a little bit more. And so again, in this class, we don't really care about the absolute numbers of things. We're going to care about the relationships between all these variables. And anytime we don't care about the actual raw numbers plugging in things, big O notation is our friend, because big O notation helps us really capture the relationship between things rather than the raw numbers. And so this term right here that I have under epsilon, I'm going to rewrite that in big O notation. First, we'll say that that's equal to, So the square root, I'm gonna apply this log to both sides here. So it's the log of 2m minus the log of delta, like that. So this is just applying the logs division subtraction rule right here, getting that division symbol out of there to separate these up into two different terms, divided by 2n. And that in terms of like big O is equal to the square root of log m on top divided by n on the bottom minus this log delta right here. And so there's a lot of things going on with this big O notation, and you really have to understand the big O notation to understand this. But again, the purpose of this big O notation, we can take out these like random constants that are just kind of obfuscating the relationship between things. And now we see that log m and n have some sort of like linear-ish relationship, that if I make my model class bigger, I can make it a lot bigger, like exponentially bigger, and I still only need a small amount of data points back. Similarly, this term over here, this log delta term, this is the whole probability factor. This over here has no relationship on the model class, that I can sort of think about this term and this term independently. And if I just know that I want like delta to be equal to, say, the 0.001, some like very, very high confidence in things. And I have, so then log delta, that'll be 10 to the negative 3. Log delta then just being equal to negative 3. The negatives will cancel out in these terms. And so the negative log delta divided by n is going to be equal to 3 over n. I don't need very many data points at all for this term over here to be like really, really small. If n is say 1,000, then my like accuracy from a probabilistic perspective is going to be very, very, very high. The only thing that's going to really matter is the size of our hypothesis class over here. So again, we'll be making this sort of more concrete as we see more examples talk about this with the infinite hypothesis class. But this is sort of like the actual like important thing to remember and apply, because it focuses on the relationships between things. Okay. So that segues us into the next set of notes. And the next set of notes starts with this thing in orange. So now we're fully in chapter 2 right here. And again, so the very top of this set of notes, it's saying the finite hypothesis class generalization theorem. That FHCG theorem from the previous lecture notes gives us this bound right here, which is exactly what I wrote on the other set of notes. And again, this is not in the book, but it follows sort of immediately from what's in the book. And somehow our goal is to have a formula similar to this that's bounding the E out EN relationship, this generalization error over here, but it's not strictly related, only useful for finite models. And what we're going to do is we're going to introduce this idea of a VC dimension, this DVC. And DVC, like the intuition of it, is it's somehow going to be replacing the log M factor up here in this down here. But whereas M is infinite for infinite models, this DVC is going to be finite. And so we'll still get good generalization results. And when we're making this decision about which classifiers we should or shouldn't use for a particular problem, we'll be asking questions about what is the VC dimension of this classifier, and how does that affect my training error versus my out of sample error versus my generalization error, and for which particular problems does it make sense to use a high VC dimension, and for which particular problems does it make sense to use a low VC dimension. In order to really get to that intuition step, though, we have to do a bunch of formal stuff defining this VC dimension. And that's what most of this notes packet and all of chapter 2 in the book is dedicated to. Any questions so far? Okay, before we get into that in detail, I always like to, so this VC comes from two people's names. And when I get like formulas or things based on people's names, I like to learn a little bit more about those people. So the V comes from Vladimir Vatnik. He is a, and then the C comes from Alexei Chervonenkis. Both of these were Soviet scientists. The VC theory that we're studying right now, they both created in the 1950s. So it's very, very old, been used for a very long time. And the motivation, the reason that they were studying this in the Soviet Union was they were using these learning models for their central planning system to decide which factories get the outputs from which other factories. At the time in the 1950s, Soviet Union way ahead of the US in terms of like statistical analysis of algorithms, but the US way ahead of the Soviets in terms of like actual computing capability. Vatnik, after the fall of the Soviet Union in the early 90s, he moved to the US and currently works, or worked for a while at Facebook. I think he left to go somewhere else. So here's him on the left over here at Facebook. And then Chervonenkis, he died in 2014. The official story, which I have no reason to doubt because he was like 90 at the time, was that he was going on a walk and just died of hypothermia, but because it's cold in Russia. But at the time when it happened, everybody was talking about how he drank too much polonium, or he got on the wrong side of Putin. Sometimes it's fun too to look at non-English versions of Wikipedia. This is the Russian version of his Wikipedia entry. You can see his actual picture and has more stuff. Because the Russians care about him more than we do, I guess. Okay. Okay, back into technical details now. Fun aside over. Okay. There's going to be a lot of technical terms that we're going to define here in order to prepare this idea of the VC dimension for us. And again, that will prepare us for the intuitive understanding of things. And the first of those terms is the idea of a dichotomy. So here we have x1 up to xn, our training set, always in the book using this notation of capital N for the number of data points. The x's are features. And this capital X right here is always like R to the D. So there's D features for each one of these data points. And normally when we have a hypothesis class, it's not a function, it's just a set. And so this is sort of like an abusive notation that if you turn your hypothesis class into a function, then it becomes a function. If it has parentheses next to it, it's no longer a set, it's a function. And the idea of this function is that we apply every single one of these h's in the hypothesis class to every one of the data points. The formal notation of what's going on here is pretty confusing because there's just a lot of stuff. And so I think seeing this example down here will help clarify that a lot. So we're going to look at these two different data points right here. We're going to look at this hypothesis class right here, and we're going to see exactly what are the dichotomies of this hypothesis class on these data points. And that will help give us an intuition for what a dichotomy is and why we care about it. First part of that is let's plot these data points. So I'll draw some like little axes right here. And then here we have one data point in each quadrant. Draw these all as just circles. Notice that these data points are only the features, only the X values and not the Y values. Whenever we're talking about the dichotomies of something, we're only talking about the features. We're not considering the Y values at all, just the features. And so here, this first data set has something in each quadrant. And then this one down here has things only in the positive, positive, negative quadrant, something like that. So two different data sets. And now this H-axis is a hypothesis class that we've seen before. And it has, when in this case, d equals 2. So it has 2 entries in this hypothesis class. It has the function x into the sine of x1. That's one of the functions. And I'll draw the other one right here. X into the sine of x sub 2. So again, this I here ranges over everything in the square bracket D. The square bracket D, again, that's equal to the set of all numbers 1, 2, up to D, all the natural numbers up to D. And so in this case, I is going to range over 1 and 2. And we'll take the sine of x1, sine of x2, plugging in 1 and 2 for I right here. And the visualization of this is that we're just cutting the data set in half by one of the planes, by either the x plane or the y plane. And scrolling back up a little bit. In this dichotomy definition, what we're doing is we're applying each function to each data point in the hypothesis class. Each function, each hypothesis, each H in the hypothesis class, create a tuple of the same size as the data point, applying the function to each data point. So for this first data set, the X data set, this will all be first data set here. If we apply this function to all of the x's, let's go up so we can see them right here, then so what we're looking for is, call this right here h1 of x1, comma, h2 of x2, comma, h3 of x3, comma, h4 of x4. This is applying this particular function to every element in the data set. And when we do this, that's going to be for x1, we're looking at the sine of the first column, the sine of the first feature right here, +1. So we'll get +1. Then here we get the sine of the second feature. Oh, sorry, it's still the sine of the first feature of the second data point. So we get -1, +1, and -1 like that. And this, again, is the result of applying this function right here to each one of these data points, getting +1, -1, +1, -1, because that's the sine of the first column over here. When I do that same thing for this H2 function, we call this H2. What I'm trying to calculate is H2 x1, H2 x2, H2 x3, H2 x4, and that's going to be equal to, in this case, we're looking at not the first column, but the second column over here. +1, comma, +1, comma, -1, comma, -1. And so the dichotomies on the first data set, the dichotomies are just equal to the set of +1, -1, +1, -1, and +1, +1, -1, -1 like that. Each individual step is hopefully not too difficult. The hard part about this is just like understanding what are all the steps here from like what is this notation trying to say. So are there any questions about why these are the two dichotomies of h-axis applied to that first top data set? Apologize for Zoom people. We'll have to get those questions answered later. So all of this right here, when I say h1, that corresponds to I being equal to 1 in this sign. Oh, yes, I see what you're saying that, yeah, I got carried away with here. All these h's should be h1s. The x's vary, the h's stay the same. All of these h's are h1s, and it's the x's that change. All of these h's are h2s, and it's the x's that change. Okay. We'll make a little dividing line here. And for the second data set, we still have the same h1s and the same h2s. So h1 being x into the sine of x1, and h2 being x into the sine of x2. What's different about the second data set is that these two hypotheses, h1 and h2, always agree with each other because the sine of x1 is always equal to the sine of x2. If we come back up here, we can see that so +1 + 1, -1 -1, +2 + 2, -2 -2. The signs of the two features always agree with each other. And so when I apply this function to every data point up here, I'll get +1, -1, +1, -1. And down here, I'll get +1, -1, +1, and -1. And the formula for the dichotomies, scroll up here in a second. The formula for the dichotomies, it doesn't say this explicitly, and actually the textbook doesn't say this explicitly, but implicit in the formula is that duplicates get removed. So I'll scroll back down here in a second, but coming back up here, because this on line 3, because this definition, all of this is inside of a set. The definition of a set is that you don't have duplicates. So duplicates get removed. And down here, because both of these two things are the same, we only include it once in the list of dichotomies. So down here, the dichotomies, probably misspelled, is only going to have a single element inside of it. +1, -1, +1, -1, like that. And in particular here, up at the top, the size is equal to 2. And down here at the bottom, the size is equal to 1. Yes, no. Down here in the second data set, I'm referring to this prime data set right here. These +1, -1, this is the result of applying the h1 to each of those particular values. So I didn't write this first line up here where it was like h2x1, h2x2, h2x3, and so on. I just wrote the result of applying. And it's not 2 ever because the sign function ignores the value and just gives us the plus or negative 1 out. Did that answer the question? Good question. Any other questions so far? Okay, this idea of like this duplicate removal, the fact that it's this set notation with this duplicate removal, that's going to be what's going to allow us with these infinite hypothesis classes to be able to make interesting statements. Because when we have our infinite hypothesis class, when we apply it to a finite data set, we're always going to get a finite dichotomy, and we'll be able to characterize the difficulty of the hypothesis class on that data set by the size of that dichotomy. Okay, this next page down here, there's a lot of definitions next that are all very closely related to each other. And the best way to understand these definitions is through an example. So the 3 definitions are the growth function, this idea of shattering, and down here, this idea of a breakpoint. And we're going to look at this example 2 right here in order to understand each of these definitions. So I'm going to start by talking about exactly what this example 2 is asking us. And then we're going to go through each one of these definitions sort of one at a time, how it applies to this example. So our hypothesis class is going to be the perceptron. So we're now into this like infinite hypothesis class. This is a meaningful thing that people actually use in practice. And for visualization purposes, we'll focus on just 2 dimensions. And the question is, what is MH3 and MH4? And so this MH3 and MH4, this is the formal notation for this idea of a growth function. So again, I'm going to just describe in words what this definition is saying, and then we're going to do an example, go through these 2 examples, and that'll hopefully help illustrate what the growth function means intuitively. So the growth function always takes an integer as input, this mh of n. And again, the capital N, anytime you see that, you should be thinking that that's somehow the size of a data set. And then it's, so this H right here is a dichotomy. This is our formula for dichotomies. We know it's dichotomies because we have a hypothesis class, and we're not just talking about the hypothesis class. We've sort of somehow made it into a function with these parentheses right here, and it's the dichotomy on this particular data set. What this whole thing inside of the absolute value symbol, that's the cardinality of this set, or the number of elements in the set, or the size of the dichotomy. So number elements in the dichotomy. And then this max over here is saying that we're going to look at all possible data sets that we could, they could possibly exist. So this is a max over an infinite amount of things. And we're going to see what is the largest dichotomy that that particular hypothesis class can possibly have on a data set with this characteristic. Not about a specific data set, but about all possible data sets. And so now we'll visualize this with the perceptron, and hopefully that'll get us some intuition for what this growth function means. If our discussion here, for whatever reason, is not making sense, and you want another source to review it, this is all just straight from this example in the book. So we're first going to consider this MH3 right here, and we're going to draw some particular data sets and look at what are the dichotomies of those particular data sets. That'll be where our starting condition is. So for Again, this 3 right here is an n. You should be thinking about that as the size of the data set. And so we'll draw data sets with 3 points. And we'll consider 2 possibilities. One where those 3 points are collinear, they all exist on the same line. I'll draw some dots here just to indicate that these are all 3 data points on the same line. That'll be our first data set. We'll call that A. And the second one, which we'll call B, will have 3 points that are sort of not at all on a straight line, forming some sort of triangle like this. And if you sort of think about it for a little bit, you can probably convince yourself that those are like somehow the I don't know, the only like examples. Every possible data set with 3 points is going to somehow be like a transformation of one of these things. They'll all either be on a straight line, or they'll all be in a triangle like this. And so the first thing what we're going to do is we're going to count the dichotomies on both of these. And in this case, the hypotheses would look something like this. We can have a hypothesis here with plus and minus on one side, or reverse it, minus plus on one side. A hypothesis here, separating these with either plus and minus on one side or minus and plus on one side. And a hypothesis here with plus or minus on one side and plus or minus on one side. And in particular, no matter like how we draw our particular lines that separate out these data points, because the perceptron hypothesis is somehow drawing lines between data points to do a linear separation between them. In particular, there's no way that I can somehow separate out this middle point right here so that this middle point is different than both of these other points. It would be impossible for me to somehow, so these 2 things are impossible that I'm going to draw right here. It would be impossible for me to get a plus, minus, plus, or a minus, plus, minus. That this middle one has to match one of these outliers. Every other possible combination of pluses and minuses we can get by some linear separation like this with pluses and minuses on some of the sides. Turns out there's 6 total possibilities of distinct dichotomies that you can get this way. And so I'll say, the number of dichotomies here equals 6. For this bottom one right down here, then you can separate out these so you get pluses and minuses however you want. And if you work that out, then the total number of dichotomies will be equal to 8. We're just about out of time, so I think this is a good place for us to stop. We'll pick up this discussion next time. And yeah, if anybody has more questions, happy to answer them after class. And again, whether it's about like midterm, if you think I made a mistake, feel free, or you just want to know more about why a problem is the way it is, feel free to ask me those sorts of questions or questions about this material here. But otherwise, I will hope you all have a great week, rest of your week and weekend, and see you next week.